Welcome back to this course on Fundamentals of Computer Architecture. The goal of this lesson is to give you an introduction to embedded systems. This lesson is based on Appendix E of the textbook by Hennessy and Patterson. This appendix is available for download online. It is also partially based on Chapter 1 of the book Embedded Computing, a VLIW approach to architecture, compilers and tools by Joseph Fisher, Paolo Faraboshi and Clifford Young. The first question that should be asked and answered is, what are embedded systems? Well, this question is not as easy as it seems. What can be said is that embedded systems are computer systems with a dedicated function embedded or lodged in other devices where the presence of computers is not immediately obvious. The question is not easy because it's quite hard to draw a clear boundary between embedded and general purpose computing. A microwave with an embedded microcontroller is clearly an embedded system. The microcontroller has a dedicated function, namely to control the microwave, and is embedded into the microwave. A desktop PC is clearly not an embedded system. It is immediately recognizable as a computer and can perform many tasks, some of which were even unknown at design time. A cell phone, on the other hand, may or may not be classified as an embedded system. You can still make wireless phone calls with it, of course, but modern cell phones can perform many more tasks. You can play games on it, you can take pictures, you can record videos, it can play music, etc. and so forth. On the other hand, it does have some embedded systems characteristics, and for that reason I will classify it as an embedded systems. Embedded systems are everywhere. They can be found in everyday devices such as watches, cameras, microwaves, toasters, washing machines, dryers, TVs, etc. Modern automobiles also contain many embedded systems controlling everything. The anti-lock braking system ABS, the airbags, the engine control unit ECU, automatic car parking, etc. In addition, there are several systems for in-car entertainment. Also, airplanes and trains have many embedded systems. Then there are handheld digital devices, the personal digital assistants, PDAs, of course the cell phones, music, MP3 players, etc. Video game consoles and set-top boxes are other examples of embedded systems. Then there are printers, network switches, modems, etc. And the list goes on and on. What this list also shows is that embedded systems have a huge range of processing power and cost. From low-end 8 and 16-bit microcontrollers that cost less than €1 to systems containing full 32-bit microprocessors capable of processing around 500 million instructions per second and cost around €10, to systems containing high-end embedded processors that cost hundreds of euros and can execute several billions of instructions per second. Many more embedded systems are sold every year than general purpose computing systems, but I could not find a figure that compares the sales of all embedded systems and all general purpose computing systems. This figure just compares the sales of PC systems, including laptops and netbooks, to the sales of non-PC systems, in particular smartphones and tablets. It shows that even if we exclude all the watches, cameras, digital TVs, washing machines, etc., more non-PC systems are sold every year than PC systems. Let me now discuss some characteristics and requirements of embedded systems. Often, but not always, embedded systems execute only one or a few applications. This enables the embedded system designer to optimize the system for that application or those applications. For the same reason, the compatibility barriers in the embedded domain are lower than in the general purpose computing domain. Because the software is sold together with the hardware, embedded applications are recompiled and sometimes even redeveloped for each new product. Second, many embedded systems have real-time constraints. That means that they must complete their task on time, otherwise it is considered a failure. I will say a bit more about real-time constraints on the next slide. Third, price is often the key factor in the design of embedded computers. Of course, there are performance requirements, but the primary goal is often to meet the performance needed at a minimum price, rather than achieving higher performance at a higher price. Fourth, because many embedded systems are powered by batteries and do not have a fan for cooling, low power consumption is another strong requirement of embedded systems. Because the power consumption increases with supply voltage and frequency, embedded processors typically have a lower frequency than desktop and server processors. Another requirement of embedded systems is the need to minimize the memory usage. In many embedded applications, the memory is a substantial fraction of the total system cost. Some architectures therefore have special instruction sets to reduce the code size. For example, most ARM processors can execute not only 32-bit ARM instructions, but also 16-bit thumb instructions. Another characteristic of many embedded systems is that the physical dimensions are constrained. It must fit in a watch, for example. It can't be larger than, say, half a centimeter squared. An important acronym in the field of satellites is SWaP, which stands for size, weight, and power. A final characteristic of embedded systems that I would like to mention is that they often communicate or interface with the physical world. For that reason, they often have analog to digital AD and digital to analog converters. As mentioned before, many embedded systems have real-time performance requirements. That means that an application or a segment of the application has an absolute maximum execution time that is allowed. If this maximum execution time or deadline is not met, the system is failed. In general, we can distinguish between hard real-time systems and soft real-time systems. In a hard real-time system, all deadlines are hard, meaning that a missed deadline corresponds to a total system failure with perhaps lethal consequences. An example of such a system is the airbag in a car. Typically, the decision to deploy an airbag in a frontal crash is made within 15 to 13 milliseconds after the crash. This figure illustrates the timing of a hard real-time system. Not only the average execution time must be shorter than the deadline, but also the worst case execution time, or WCET. In a soft real-time system, on the other hand, there are some deadlines that are soft, meaning that it may be missed occasionally. An example of such a system is a video player or a digital TV. It may be annoying that a frame is not decoded and displayed on time, but it's not lethal. This figure illustrates the timing requirements of a soft real-time system. The average time and most execution times must be shorter than the deadline, but the worst case execution time can be longer than the deadline. Missing a deadline, however, should happen rarely. Given an application, the embedded system designer should select the technology to implement it. I will now discuss a number of implementation alternatives. The first option is to select a general purpose processor such as an ARM processor. General purpose processors are very flexible and can be used to implement embedded applications, but it may not meet the performance requirements of the application. The second option is to develop an application-specific instruction processor, or ASIP. An ASIP is a processor whose instruction set has been tailored to benefit a specific application. There are commercial tools to design ASIPs, for example, Processor Designer from Synopsys and Codesip Studio from Codesip. The third option is to employ reconfigurable hardware, in particular field programmable gate arrays. FPGAs can exploit all the parallelism there is in an application and therefore achieve higher performance than GPPs and ASIPs. Implementing and optimizing an application on an FPGA, however, can take a very long time. The fourth and final option is to develop an application-specific integrated circuit, an ASIC. An ASIC is an integrated circuit customized for a single particular use. Developing an ASIC, however, takes a long time and incurs a high cost. The non-recurrent engineering or NRE cost of an ASIC can easily run into the millions of euros. ASICs are only cost-effective if many devices will be sold. In general, if we go down this stack of design alternatives, the performance and power consumption improve, but the flexibility decreases. Finally, an exercise. This exercise asks you to give a definition of embedded systems and to explain the difference between hard and soft real-time systems as discussed a few slides ago. This completes this lesson. Thanks for watching. In the next lesson I will start a new module in which I will describe the MIPS 64 instruction set architecture. Hope to see you back.